So allow me to introduce myself. My name is Aurélien Wailly. I'm a last year PhD student working at Orange Labs, and my research is about, well, self-defending mechanism for cloud computing environments. And during my research, I asked myself how malwares are detecting virtualized environments. So first, if my English is not really correct, you can raise your hand. I will try to do slowly and with a better pronunciation. Still correct? Or you didn't understand me? But I'll try. First, if you are partially sighted or something like that, you can grab the slides on my website, so flash with QR code. You can grab it on this URL. You have also the PDF version. I will leave you few seconds to do it. It works on your phone and everything. Is Wi-Fi working? Yes? Okay, it's my computer. Okay. Okay, so today I will follow this outline. Where are we today with malwares? What is the research environment? As I told you, I do a PhD, so I'm academic oriented. I will show you papers, the most important papers, how to detect virtualized environments, and how to hide from detection, and how to detect hidden environments, and everything. And finally, I will give you a roadmap, or what is the next step into this war, and what we will expect. First, virtualization. Why we use it? For easy provisioning, meaning that I need a Linux server in a few minutes, I can have it. I can roll back if I do some malware analysis. I can infect my computer, and in a few seconds or minutes, if you have a big machine, you can roll back to your safe and clean version and do it again. You study your malware again. All right, this is for malware analysis, but you can also consolidate. This is the cloud computing era, meaning that you have 10 servers with 10% load. You can gather it on one server with 100% load. You will cut costs off. You can also have a fine-grained resource control, meaning that you have a small machine because most of the time you have 1% load, but you have been retweeted by someone and you have 80% load on your machine. It's okay. You have 200% load on your machine, you have a problem. So you can create another server with a template and have load balancing among them. You need more RAM, you will have more gigabytes, you need more hard drives, you will have more, and you have fine-grained controls. But it's still rarely used, and it is often the sign of an analysis. So if you see that you're under virtualization, it means most of the time that you are being analyzed. Not a good sign. We can use it on the bright side of the force as an easy sandbox with a VMware player. I think most of you know VMware player. Raise your hand. Yes, you understand my English. Pretty cool. But it will leave no traces. You can roll back whenever you want. You will be cool. You can debug kernels. If you had debugged kernels once in your life, you know that it's pretty hard to do. When you do a mistake, a seg fault, you have to reboot, wait 10 minutes because you're on a server, and do it again, all over. It's also pretty cool to try other OSs, operating systems. You can have your Linux on your Windows, and even your Windows in Linux in your Windows, and furthermore. On the dark side of the force, we can intercept what is behind the OS and the physical components. Meaning that I have my operating system now, my Linux. Blue pilling a system, it means that my OS will be virtualized hotly during the run, and it will intercept and hide himself with processor facilities. I will speak more about it later. It is also the ultimate obfuscation because it's done to be hidden. So it's mainly for testing purposes. Virtualization is for testing. On the malware side, they are largely detected. You should know sandboxes such as Anubis, Malware, GFI, malware with QQbox. Pretty sure you know it. Okay, they have adaptable behavior, meaning that if they are virtualized and analyzed, they will just open a calculator, so it's clean, bypass the sandbox. If it's not, they will drop a backdoor, easy. Also, a few weeks ago, Alex at Stick recommended to malware writers a list of recommendations such as seek memory usage versus disk usage, use custom crypto, watch for logging, watch for debug, and VM detection. This is what we will do today. So on the bright side, malware may detect virtualized environment, they adopt clean behavior, and we can do targeted attacks, meaning that I am on KVM virtualization. If I want, I can use Nelson Elage exploit, if it's still working on your computer, and exploit the KVM below. So just a simple, you understood. You have 1 arrow if you are on a clean machine. You have 1 arrow if you are on virtualized environment. All right, on the dark side. So we had the virtualization layer, the green part below. We had the malware, the red part, the bad one, up. On the other side, we may imagine games. So let's say an MMORPG with a cheat engine detection that do not want a bot to play for you. So the game is the red part, the green part, the good one. We can bypass cheat engine detection and bypass protection against fake hardware. I'll give you some schemas. The first one in red is what happens on your operating system. So my cheat bot sends keystrokes and mouse moves to the kernel with APIs and send it to the game. Pretty easy to detect it. You can find some detour and you're ready to go. On the other side, the second line, you have the same with VMM, the hypervisor, virtualization layer. So my cheat bot is on the hypervisor. You will send keystrokes with interrupt vectors. You will send it to your VMM that will send it to your game. The game cannot see you. So this is the ultimate cheat engine. So who is leading? We have on one side malware versus malware study detection, and we have games against virtualization bots. Or even how to detect virtualized environment. Is it easier to hide or to detect? First, to be clear, I will do a targeted escape against QQ sandbox. I tried a week ago, it was pretty easy in a few minutes. Sandbox environments have to extract executable actions, find what it's doing, find the environment, find the registry modifications, and send it to the login server to have debug and results. So I simply send it. This is a screenshot of the sandbox on malware.com, and I've listed loaded DLLs for my program. So you can see anti-QQ. Wait for it. Yes. Here, and you can see the list of DLL. Can you see the weakest one? Nope, because you are partially binded. Here, you have a random DLL with a random name, high entropy. In fact, QQ, when it's loading your program for analysis, will pause it before it's loaded, inject its DLL with a random name, then resume your program. So we'll have a high entropy DLL name and the lower address base of the executable. So it's pretty easy to find. you find the first loaded DLL. If you look for entropy, if it's high, you know that you're under cuckoo. Pretty easy. I'm not a wizard, just listed DLLs and find entropy. Up, late, here. But we will go deeper. What we will find in the next slide, it's how to do it with the generic way, meaning that you can detect your virtualized under cuckoo, under everything, just the VMM layer. So first, virtualization, you have no more CPU, you have a virtualized CPU. You don't have memory, but another MMU layer. Inside the CPU, you have information tables, and each processor have its own IDT. IDT stands for interrupt descriptor table. When you move your mouse or you put the keystrokes, it sends an interrupt to your processors, and your processor executes the associated function. You have the LDT, GDT, local global descriptor table. And the problem is that when you have virtual CPUs, you have multiple IDTs. Where to locate them in memory? This is what Joanna found 10 years ago with the red pill. I think you know it. I will go from 2004 to today during the slides. And in fact, on a bare metal physical machine, when my IDT is around 0x80 for the MSB, I know that I'm on bare metal. If I am above OXC0, I know that I'm being virtualized. So we will analyze this IDT address to see if it's still working today. We will also see processor features such as the processor branch string with the CPU ID leaf OX800002. And even better, the CPU ID contains the is hypervisor present bit. CPU ID leaf 1, ECX, and one of the bits. We will see it also if it's working. We can also measure virtualization overhead. So a small example, we will jump to the address 1000. We'll go through the virtual MMU. So virtual address 1000 to 81,000 physical address. We will go to the real MMU for the virtual machine. So it will become a virtual address, and you will have the final traduction to big number. And the arrow below, it is without virtualization. You will jump directly from your virtual address to your physical address, and you have less overhead. So we will measure VM entry and VM exit costs, and we will see how to measure it. So first, I will start with the well-known one with the translation look-aside buffer. I think you know it. You will cache your virtual to physical address translation. So you want to jump to 1000. You will ask the CPU will account the MMU. The MMU will look into the TLB, and the TLB, if you have the mapping directly, it's returned. You have a fast TLB hit. If you have a TLB miss, meaning it's not in the 64 lines of the TLB, you have a page walk. A page walk is expensive. You will go through C, R3, and all the page tables to find your translation. So we will use it to measure virtualization presence. All right, virtual memory has peculiarities, such as flushing TLB while VM exit and without having hardware-assisted mechanisms, but how to use them to test VMM presence. VMM is hypervisor. First, we will fill the TLB. Then we will generate VM exit. VM exit is when you go outside your virtualized environment. We'll modify one of the TLB entry, compare access time. Okay, let's give some schemas if you're lost. So you will do different memory access. So jump 1000, jump 2000, jump 3000 until you fill your TLB. You can have Yes, you can find informations inside your CPU ID leaves. So here I'm cheating, I'm using CPU ID, but you have your TLB size. So 32 entries, 16 entries, depending on if it's data or instructions. All right, so we gather this. We do enough memory access to fill the TLB. The TLB contains only our translations. Up. Then I measure how much time it takes to go through all these addresses. So let's say we have a round trip time of 400. I keep it, I save it. Then I do a VM exit with CPU ID. CPU ID, as you know, is the non-virtualizable instruction from Popek and Goldberg. You can click on the slides, there are some links. All right, so the CPU ID will call the VMM. The VMM will do some memory access because it has variables and own stuff. It will modify the TLB with at least one entry. So the VMM address 7000 to a new mapping. I have a modification of the TLB. And when I go back to my VM, I will measure time again, except that I will have a page walk with a TLB miss for at least one address. So we can compare the time directly with 400 being lower than 900. We know that we are virtualized. I gave you the 400 and 900, but what is the meaning of this number? How to benchmark? For benchmarking, you should know timestamp counters, such as read timestamp counters, or the precise version with RDTSCP, not present on every processor, but coming. You have a link to do it very well here. You can click, I won't. Oh. You can use real-time clock with dev@co. You can use periodic interrupt timer, but they are pretty bad precision. You can also use high precision timers with higher frequency, 64-bit resolution. Okay, you can also use external timers to be sure of your source. And you rely on external protocols such as NTP and simple NTP, but they are really not precise. There is a ratio of 1,000 between read timestamp counter and NTP precision. Also, if we want to cheat against NTP, we can simply parse the NTP packet and add the offset that we want to hide VMM presence. Or even better, without timing reference, simply do a ratio. We will create two counters and compare their values. So we take one thread that we put on one core with only CPU ID. So we will do VM exit, VM exit, VM exit, VM exit all the time. It will take a huge amount of time to be treated. Then we will do a thread on another core with only NUP. So you have two loops. One loop with only VM exit, one loop without VM exit. We will compare the time and see if its ratio is good or not in the following slide, but you got the idea. Also, you can find discrepancies. Processors does not produce the expected behavior. I'm pretty sure you know the proof bug with wrong emulation. Intel does not produce the expected result from the manual, but another. So we had specification updates for manual and what is actually happening on your processor. You have also the SMSW instruction, which says that you will store 2 bytes on the lower byte of your register, say EAX, but the 2 most significant bytes have undefined behavior, so you can put whatever you want. We will do MOV EAX, OXCC. We will do SMSW EAX, and we will see if the first OXCC have been overwritten or not. We understand in the next few slides. Also, we have specific hypercalls. This is a nightmare for VMware backdoors and VirtualBox 1. For accelerated graphic and drag and drop, also highlighted by Peter Ferry, if you know them. Yes. Typical attack, oversized instruction. On Intel, you cannot pass an instruction with more than 15 bytes. You know you can use the repetition prefix to do it. On VirtualBox, I think it's VirtualBox, it will simply handle the instruction, do nothing, and give you the hand. On a real Intel CPU, it will generate a fault. So you can detect again. And this is time for the demo, but I use my backup slides because there is no Wi-Fi for me. Hop. So I'm on bare metal. This is my base for all the remaining tests. So firstly, here, this is a processor brand string, so Pentium dual core, old machine. The IDT base around with the most significant byte here, 81. We have the easy hypervisor present. So I take CPU ID, leaf1, ECX here, and the good bit in ECX. The MSW, here we can see that CC has been overwritten. And we have the ratio. You remember the two loops. Okay, so a good ratio on my bare metal machine is about 200. Then we will go to VMware Player. The brand string is still correct. Dual core. IDT base still correct also. We have the MSB 81. CPU ID hypervisor present. Say yes, I'm present. I'm an hypervisor. MSW is correct, but the ratio 1500, meaning that when I do one CPU ID, I do 1500 NOP. You know that you are under VMware. And we will see that this ratio is able to give you a nice signature of your virtualization environment. So let's do it on the VMware Type 1 hypervisor. This is Type 2, as you know. ESXi, the Type 1. So here I'm on a real server with a Xeon or something. The brand string is still correct, the IDT also. So recognize virtualization with IDT don't work anymore. You have the is hypervisor present bit still at 1, easy to find, but the ratio is pretty good here, 600. Not as my bare metal, but we can detect it easily. Next, QEMU. Pretty strange behavior because the ratio is still weird. I will explain it now. But yes, the processor brand string reflects QEMU directly, so we know that we are under QEMU. IDT base is correct with 81, so it's still not working. Hypervisor present, we have a bit 1. MSW, this time, as we do emulation, has not been overwritten. So the emulation undefined behavior respects the manual, but we don't have the same behavior on the real processor and on CPU, QEMU CPU. And the ratio, below 10, 3, meaning that when I do one CPU ID, I do 3 NOP. Why? No, you don't. Because in fact, QEMU will use translation block, meaning that you will go to a basic block and you will save. When you go to this address, you know that you will have this result. So it computes CPU ID once, then you remember the result, and when you call CPU ID once more, you will have the result directly. So just a ratio of 3, pretty good. We will go to the cache. There is a cache of instructions, and we are ready. All right. The accelerated version of QEMU with KVM, which use QEMU for device management, such as Xen. We have the same processor brand string. We have the most significant byte of IDT still at 81. Okay. Hypervisor present bit is at 1. MSW is correct, but ratio this time we don't have the translation blocks. We use the hardware facilities is above 900. So we had 600 for VMware. We have 900 for KVM. We can detect exactly what is the hypervisor. Finally, Xen with the processor brand string reflecting Xeon. we have the IDT, which is correct, the CPU ID reflecting 1, the MSW, correct again, and we have a ratio of 681. So you understood. We have all techniques, such as red pill not working anymore, but our ratio gives you exactly the virtualization environments that you are on. Also, for Peter Ferry, I tried several of these techniques, but it's pretty long to do it, and I didn't have the time yet. Also, I come from the academic world, so I like when stuffs are formalized, and I found some papers which formalize VM detection in 3 categories. Logical discrepancies, meaning that you have unexpected CPU behaviors. As explained before, you have resource discrepancies, such as the QEMU hard drive, which is named QEMU, pretty easy to find. You have the string VMware in Windows registry for VMware player, as example. And you have timing discrepancies. I showed you the ratio, you have VMM overhead. How to find them? You can use random tests, do it manually. If you have luck, you will find them, exploit it. You can automate them, I will see it in the next slide. Or you can learn from one fix. Think as Tuesday patch from Microsoft. Julia explained yesterday better than me. Intel published specification updates such as the FOOF bug. So you know what are the discrepancies that won't be patched for each processor. I will show you PDF of 2 specification updates just to see if it's still up to date or not. Here you can see the Pentium 4 no fixed discrepancies. Sorry for the resolution. And you can see that there are many won't fix. There are about 3 pages. And yesterday I found the same for the latest i7 core. Not the as well, but Ivy Bridge. Up. Here we go. Here. So we had 3 sheets of no fix. And now, I'm not cheating, this is the specification from June with the 3rd generation, I think Ivy Bridge. You have now 5 pages of one fix. So you directly find discrepancies from Intel. They told you, we won't fix this for this processor, you just have to wait and to use it for malware for virtualization detection. Right. I speak about using CPU to find discrepancies. I speak about devices name and resource discrepancies. What about using network? Using network, when you will do TCP with, you will send a TCP packet, the runtime trip will differ for virtualized environments and without, because you will have another stacks of IPs to go through. So you have a difference. I won't put it here because I don't have the time. You can also mimic virtualization to evade malware infection, meaning that I'm on my real OS. I don't want malware to infect my machine, so what will I do? I will copy the virtual environment discrepancies and put it on my machine, such that when a malware comes, it thinks it's virtualized, and it will just adopt the clean behavior and don't infect my machine. Also, there is a taxonomy by Chen. You should know it if you are in the academic, which was extended by Mr. Lindhofer. You can click on here, taxonomy. Also, for automatization, you remember firstful of red pills. You have an instruction that you will send on bare metal and virtual machine. The same instruction, you will ask the CPU to execute it and see the states after to see if they are the same or not. If they are the same, the malware is not aware. Oh, it's the next slide. you don't have a discrepancy here. Create similar contexts and compare results. And with that, they were able to find 20,000 discrepancies, not unique, in few hours. Quite fast. With the same idea, instead of sending an instruction, we will send a malware. Sending a malware to bare metal and virtual machine. And through differential analysis, we can compare a malware state after being run on virtual CPU and normal CPU. And in fact, less than 2% of malwares try to detect virtualization. Only the worst use it. So if you are trying to look for malware detecting virtualization, you are looking for that. And if you find one, send it to me, please. It's pretty hard to find. Thanks, Sebastian, for the one you send me. But if you have more, it will be a pleasure to study it. I've speak about the detection part. What about the hiding part? We had also, as I've said before, for detection mechanism formalization with ATER. ATER, maybe you know it. All right, it formalizes the detection methods and anti-detection methods and proposes the first architecture and implementation named ATER, which consider unexpected behaviors and set up several countermeasures, such as modify CPU registers to hide its impact, use shadow page tables, which are not under the control of the VM, and prevent timing with TSC offset, which is a feature with VTX. Also, we have the least, you should know if you are doing security, the least privilege principle. We are trying to apply it to virtualization, and to hinder virtualization effects, only vital components are virtualized. Otherwise, if they are not needed to be virtualized, they are passed through. Think about your graphic card. If you are going to use accelerated graphics, you can give pass-through to your graphic card. There is no need for virtualization. The problem is that it only supports one VM because you cannot share two graphic cards between two virtual machines. So you have to choose, in fact, between security and virtualization features because here you've lost consolidation. And it reduces hypervisor footprint. So we are going to start saying about physical virtualization or physicalization, which is virtualizing without using virtualization. So the example is Bearbox. I found this, I can show you after. It supports snapshots. It uses volatile memory, meaning that it boots your Windows OS, say on a physical machine. You have a meta OS, close, which will save the state of the machine when you are in early Windows boot with registers, with volatile memory, RAM, hard drives, store it in the first hard drive, and stop to write on it and only have read access. So it saves machine stats, machine state, register, and interrupt. The idea. It allows quick rollback, reboot on a clean machine below 4 seconds. In fact, you have a second hard drive taking the end after the boot. The malware is executed, impacts the second hard drive, and when you are done with it, you will roll back to your first hard drive state, put registers and interrupts to the last state, and you're ready for a new analysis. So this is the best rollback that I've seen for physicalization under 4 seconds. You can also patch defects, MAVMM for malware analysis, VMM, avoid TLB flushing with new VTD, VTD for hardware-assisted virtualization for memory. And the awesome part with this one is the available code. ATER was not available. This one is available, so we can use it, patch it, modify it, understand it, detect it. But it's cool. So we have new architectures, virtualized without hypervisors. Speaking about virtualization with ATER, But we have also research papers such as No Hype. You can click if you took the, you have the address here, right? You have also D-Hype. Maybe you know the Xen disaggregation paper. All right. You have components that are going to user space if they are not vital. D-Hype is the same for KVM. KVM, as you know, is in the mainline branch of the kernel, so it's more used than Xen now. You can use it with D-Hype to protect it. Also, new architectures are pretty expensive to deploy, so even if it's, they exist since 2009, they are not widely deployed, and we are also trying to protect without new architectures. One idea is to slow CPU. You remember the two loops from before? What we will try to do is to slow down the CPU, such as when I do one NOP, it will take the same time as when I do one CPU ID. All right? But our research showed that you need to slow down your CPU by 25,000 times to hide VM exits overhead, not usable today. Also, for detection, calling thousands of VM exit is dubious, pretty strange. Usually, on a normal machine, you have 0 CPU ID per second, never. And calling thousands of them, it highlights and you can be spotted. So the rootkit to hide virtualization detection, set up a threshold, let's say more than 1,000 CPU ID per second, and hide the VMM when hit. So when you have more than 1,000 CPU ID per second, you will go outside, just set everything pass through, and after a few minutes, you will go back to take hand back on system. Also, you have the Intel as well architecture. Maybe it will be out in June. So I don't have tested it, but I took some schemas from pcworld.fr, and you can see that the round trip is below 500 cycles, but it's not enough to bypass the ratio detection. So we will wait, I think, again, 2 new architectures before this mechanism of detection will be old. It reduces ratio and time-based attack reliance. So, what is coming next? We are going toward CPU containing the hypervisor. In fact, we add software virtualization with VMware Player and QEMU. Then we add para-virtualization to virtualize non-virtualizable instruction. Then we had hardware-assisted virtualization. And now we are going, in fact, closer to the physical component. We think that the next step is to put hypervisor directly into the CPU with a new microcode. Huge impact, huge TCB, Trusted Computing Base. But several papers appeared this year to do this. We have also countermeasure with Nether, and they proved that even if Ether was formally correct for anti-detection mechanism, practically there are weaknesses. So still, if they have think about timing discrepancies, there is a 4% overhead, and we can detect it. Okay, you have the PDF here. I can explain it in a few minutes, but it's okay. So my conclusion, should we need detection? Today, we are moving to the cloud computing era, so every server is going to be virtualized. We are saying that since 2009, 2010, but today, we are not all on virtualized environment. Some say yes, we will go to it, and you have billions to win. Some others say no, you will always have a computer, a real computer on your hand. I'm split. I don't know which one to choose. So should we need detection? If you have the answer, I will be glad to speak with you. And we have also new challenges for physical hypervisor. What are the threats to put new microcode into the processor? How to do it well, and how to prevent security weaknesses. Thank you, everybody, and if you have questions. Also, the other speakers didn't have any questions, so no.
How stable is the ratio across the different CPU architecture?
Oh, what's the?
The ratio, le ratio.
Yes, thank you. But the example given before were on different CPU architecture.
And the ratio was different?
Not so much. No, really not so much. In fact, if I go back to this one, we can see the ratio. In fact, this is the ratio, the CPU exit cost. And if I go there, you won't listen to me. But I tested on these two architectures. So it's not really different. I don't have a PC old enough to go here, but it was almost the same. My computer here is violet and purple. And the Xeon, the server, as I tested the other, is the cyan one.
So to achieve current detection, you would first test the CPU, the name. According to the name of the CPU, you would expect a specific ratio, right?
Yeah.
Okay, thanks.
Yeah.
Hello. My question is regarding one of your...
Excuse me, can you raise your... Yeah, thank you.
My question is regarding one of your previous slides. You were saying about the virtual memory to physical memory mapping, and my question is, were you able to, like, if you consider a DOM 0 and there are multiple DOM use, were you able to access data which is not supposed to belong to this DOM U, like through a mapping which will take the memory of another VM?
Yeah, you can. I don't know if you've seen the recent part demo of January at CCS, CCS, where you can extract private SSL certificate from other collocated VM.
But even while using the IOMOU chip, is it possible?
Yeah.
Okay. Thank you.
I invite you to read the Thomas Ristenpart paper of January on CCS. All right, thank you, everybody.